There's a very straightforward application of the divergence theorem, but I'm hoping that its simplicity, its straightforwardness, will help to really underscore the conceptual understanding you should have of the divergence theorem. So we need to verify the divergence theorem for the vector field F is xi hat plus yj hat plus zk hat. S is the surface, is the unit sphere. So, okay, we are just going to be doing the unit sphere centered at the origin here. Xi hat plus yj hat plus zk hat. This is going to be corresponding to an expanding gas. At every point that you are this vector field is pointing away from the origin, and the further away from the origin you are, the more it's pointing away. So just as an example of that, if we were to do, what is f of the point 1, 1, 1? Well, that just is the vector 1, 1, 1. So at the vector 1, 1, 1, you're again pointing out away 1, 1, 1 from the origin. And so this fact that's kind of corresponding to expanding gas, we can verify that. We can see that by computing the divergence of f. And what do we end up with here? The x partial derivative of x is 1. The y partial derivative of y is 1. And the z partial derivative of z is 1. And so add all of this up, we get 3 as the divergence. Things are expanding outward because the divergence is positive. And let's see here. So we've got the divergence. Now it's time to actually do some calculations. So let's do this side first. Triple integral over the sphere of the divergence. So the triple integral over the sphere of the divergence. Well, okay. This region is going to correspond to spherical coordinates here. Theta is running from 0 to 2 pi. Phi is running from 0 to pi. Rho is running from 0 to 1 here. Of 3, rho squared, sine phi, d rho, d phi, d theta. And this integral is going to give us, let's see here, we can split off the theta from 0 to 2 pi d theta. That will give us a factor of 2 pi. And then we'll have integral theta from 0 to pi of sine phi. Sorry, I said theta, I meant phi there. Sine phi d phi. And then the integral rho runs from 0 to 1 of 3 rho squared d rho. That will be rho cubed. Plug in rho runs from 0 to 1. So this will give us 2 pi times 1. And then the integral of sine phi from phi is equal to 0 to pi is going to be 2. And so we end up here with 4 pi as our answer on the right side of the divergence theorem. For the left side, we need to parametrize the surface of a sphere. Once again, here's our choice here. Here's our chart. And we've got this as our parametrization, and this is our normal vector using r is equal to 1. So, okay, let's see here, f dot n d sigma. So as I said here, our parametrization is going to be cosine theta sine phi, sine theta sine phi, and cosine phi. And the cross product is going to be sine phi times this. So cosine theta sine squared phi, and sine theta sine squared phi, and sine phi cosine phi. Okay. F of r of phi comma theta. Take our parametrization and plug it in to our vector field x, y, and z is going to be, well, it's just go, we replace x with this. Well, that's just going to be cosine theta sine phi. We replace y with this right here, sine theta sine phi, and we replace z with this, cosine phi, and then we do a dot product. We do f dot with the normal vector here, the cross product. And so we have this times this, which gives us cosine squared theta times sine cubed phi, plus this times this, sine squared theta times sine cubed phi, plus this times this, which is going to be sine phi cosine squared phi. Realize that these first two terms are sine cubed phi times cosine squared theta plus sine squared theta. So that just is sine cubed phi plus sine phi cosine squared phi. So this integral ends up being the double integral, our normal natural bounds for spherical parametrization. Theta will run from 0 to 2 pi, and phi will run from 0 to pi of sine cubed phi plus sine phi cosine squared phi. Now, if you crunch things out, the integral of sine cubed phi as, let me make sure I get this right here. I don't want to speak too hastily here. We need to end up with 4 pi as our answer. So there's no theta dependence here in this integral. So our answer is going to be, this integral just becomes 2 pi times the remaining stuff here. Phi runs from 0 to pi of sine cubed phi plus sine phi cosine squared phi d phi. And in the interest of time, I was going to skip over the details, but I think we can evaluate this. How am I going to evaluate this? I'm going to factor out a sine phi factor here. And magic is going to happen. So we end up with sine phi times sine squared phi plus cosine squared phi d phi. Hey, I think this is equal to 1. And so now we're just left to integrate sine phi from phi is equal to 0 to pi. So we have 2 pi times 2. And so sure enough, we get 4 pi, which matches what we had before. So straightforward verification here, but I want to kind of emphasize the physical aspect of this. If we're thinking of this as an expanding gas, the gas is moving away from the origin. We have some kind of explosion here. Well, the divergence here is positive, and if you do a triple integral of the divergence, you get 4 pi. But also, our flux integral, all of these calculations here, we end up getting something positive. This says that the net flow outward through the surface is positive. Well, and that makes sense. If you have an expanding gas, of course, stuff is going to have to be moving outward through the boundary there. That makes sense.